projectile motion problems really deserve a couple of examples. When you do projectile motion problems, there are three things to remember. First of all, what's happening in the x direction and what's happening in the y direction are independent from one another. Secondly, the acceleration in the y direction is known. It is negative 9.8 meters per second anywhere on Earth. And thirdly, the acceleration in the x direction is 0. This is true for any projectile, and it is only true for projectiles. You want to be careful not to take these pieces of information about the acceleration in the x and the acceleration in the y and assume that those are true in other types of problems. In other types of problems, the motion in the x and the y is still independent of one another, but you don't want to accidentally slide that negative 9.8 meters per second into some question that's not about free fall. So let's give a couple examples here and see what we can do. Example number 1, an airplane is moving horizontally with a constant velocity of 115 meters per second in the positive direction at an altitude of 1,050 meters. The plane releases a package that falls to the ground along a parabolic path. Ignoring air resistance, find the time required for the package to hit the ground. Okay, what's not spelled out super specifically here is that if the airplane is moving at 115 meters per second, then the package is moving 115 meters per second inside the airplane in a positive x direction prior to it being dropped. All right, let's take a look at what we need to do. Step 1 for any problem, draw a sketch and list out the givens. So I've got a little airplane and a package being dropped out of it, and it says it's going to fall in a parabolic path. Parabolic path just means it will never actually be vertical. This box is moving to the right at 115 meters per second, and because the motion in the x direction is independent of the motion in the y direction, and because the acceleration in the x direction is 0, it will never stop having a rightward motion. So if you sketch out the trajectory like this, you want to make sure it never actually becomes vertical. Here are the knowns. I know in the x direction, the initial velocity is 115 meters per second, and I know that the acceleration is 0 meters per second. In the vertical, I know that the initial velocity is 0 meters per second because the crate was flying in an airplane traveling horizontally. It was not moving up or down initially when it was dropped. We know the acceleration, negative 9.8 meters per second. And we know the altitude was 1,050 meters, but we want to be careful about this. It's not going from 0 to 1050. It's going from 1050 to 0. So the change in its position in the y direction is negative 1,050 meters before it hits the ground. Okay, so I want to calculate the amount of time it takes to hit the ground. Do I have enough information to do this? I don't have a whole lot of information in the x direction, but I actually have a good amount in the y direction. I think I could use that equation that does not have v final anywhere in it. So I start out with the equation. I substitute in the numbers that I know. The delta y is negative 1050 meters. The v initial in the y direction is 0. 1/2 acceleration times time squared. I can calculate this, and I get that the amount of time that elapses before the crate hits the ground is 14.6 seconds. Notice all of this calculation happens in the vertical direction. It doesn't matter what's going on in the horizontal direction for this problem. This could have been out of a hot air balloon that had no sideways velocity, and the amount of time it would take to hit the ground wouldn't have mattered. However, for example, number 1 continued. For the package in the last example, find the velocity just before the package hits the ground. The interesting thing about trying to calculate the velocity is a vector. Looking at that drawing in parabola, it will have both a down component and a rightward component when the package gets to the ground. So I will need to determine the final velocity in the x direction and the final velocity in the y direction and then combine them. The final velocity in the x direction is actually going to be really easy because the acceleration is 0. So that equation x final equals x initial plus a delta t is just a rearrangement of the definition of acceleration, delta v over delta t. The final velocity in the x direction is the same as the initial velocity in the x direction because it experienced no delta v because nothing happened to it in the horizontal direction. So that's pretty easy to do. And notice up in the top right corner here, I just drew in a vector arrow to represent the final velocity in the x direction. Now I'm going to calculate what the final velocity in the y direction was. I'm going to use this equation. This is the one I was just saying I rearranged over on the left. I'm using it here to calculate the y direction final velocity, which was 0 meters per second as the v initial, and then the acceleration and the time I'm plugging in right here. And I'm getting v final in the y direction is 143.46 meters per second, and it's negative, meaning it's pointed down. So I've drawn the arrow pointed downward here. In order to add these two vectors, I need to draw the second vector arrow tail to tip from the first vector arrow. So with displacements, this was really obvious that you would walk a certain amount to the west or the east, and then you would walk from there a certain amount north or south. And so drawing the second arrow from the end of the first arrow made a lot of sense. With velocity, it's not always obvious to people, so I'm emphasizing to you right now that we still do it the same way. My final velocity, the combination of the two, will be from the origin of the first vector arrow to the end of the last vector arrow. This now makes a right triangle, so I can find the magnitude of that using the Pythagorean theorem. And I get 184 meters per second. I get that it is at an angle theta below the positive x-axis, so I've marked theta on my drawing, and I need to calculate for it. I'm going to go with the fact that tangent is equal to opposite over adjacent, and the opposite side is the blue arrow, that's my Vy final, and the adjacent side is the red arrow, that's my V final in the x direction. So my theta comes out to negative 51.2 degrees. So the final velocity of the package, just as it's about to hit the ground, will be that it's traveling at 184 meters per second at an angle 51.2 degrees below the x-axis. All right, let's try example 2. A stunt car is launched from a 30-degree ramp at a speed of 38 meters per second. How long will it be in the air? And when it lands, how far to the right will it be from the end of the ramp? The drawing gives us that the landing area is sponsored by James Madison University, apparently, and is at the same exact height as the end of the ramp. So it's not spelled out in the question, but the drawing is telling me that the total delta y will be 0 by the end of the trip. So the car will go up high and then come back down. Okay, step 1, draw a sketch and list the givens. I don't need to draw a sketch if it's given to me with a picture, so we could jump straight into listing some givens. In the x direction, the horizontal direction, I know the acceleration is that there's none, and in the y direction, I know the acceleration is negative 9.8 meters per second, and as I said, I know that the displacement is 0. What about v initial? Isn't that given in the question? Yes, it was given that it was 38 meters per second, but what direction was that? The 38 meters per second is up the ramp. It's not in the x direction or in the y direction. It has a x component and it has a y component. So I need to find, I'm drawing in here down by the car, an x component, that's the v initial in the x direction, and a y component, that's v initial in the y direction. I can't do any math with the 38 meters per second until I have broken it apart into how much of it is in the x direction and how much it is in the y direction. So to find the x component, I'm going to point out that cosine theta is the adjacent over the hypotenuse for any right triangle, and our theta, that is between the hypotenuse and the adjacent there, is the angle that we were given, the 30 degrees. So I can find Vx initial this way. I rearrange it and come up with Vx initial is 32.9 meters per second. I can do the same thing to find Vy initial, except I'm going to have to use sine theta. That's okay. Vy initial is 19 meters per second. And I want to double check before I move on. Are these both positive? Have I lost a negative anywhere? No, one's in the positive x direction, one's in the positive y direction, so I'm in good shape. And I can go to start listing these in my givens. So I've added these to my givens. I've also added one other thing to my givens. Notice in the vertical direction, I added a Vy final is negative 19 meters per second. That's because this is going to be a symmetrical path where the car goes up and then comes back down, and it will land at the same height that it started. So because delta y is 0, my Vy final will equal the negative of my Vy initial. So I'm putting that in as a given here at this point. It's not really given, but it definitely wasn't something I had to calculate, so I think it counts as given. If you say, I know this because of the symmetry of the problem. All right, now I can calculate the amount of time that it's in the air, and I can calculate how far it goes in the x direction, and I just have to make sure that I keep what's going on in the x direction separate from what's going on in the y direction. Okay, the acceleration in the y direction is known, and the change in velocity in the y direction I can determine from v final minus v initial. So from that I can determine how much time it's in the air. Delta t will be equal to v final in the y direction minus v initial in the y direction divided by the acceleration in the y direction. So if I'm careful with my negative 19 meters per second, v final in the y direction, minus 19 meters per second, which was v initial, divided by negative 9.8 meters per second, I get that the delta t is 3.9 seconds. If you drop a negative in this math, you are likely to come up with delta t equals 0, and you know that that's not the answer you want. So if you come up with a 0 and you know that that doesn't make sense for the question, go back and double check to see if you've dropped a negative somewhere. That's frequently what's happened. Now that I know 3.9 seconds is how long it's going to be in the air, that's the one piece of information that can go from the y to the x. I said we have to keep what's going on in the x and y separate, but the amount of time it's in the air is the one thing that ties the two dimensions together. So now I can say the velocity in the x direction is delta x over delta t. The velocity in the x direction is just the initial velocity stays the same the whole time. So I can treat it like it's an average velocity. Here it is. And I can take the 3.9 seconds that I found on the vertical part of my calculations here, and I can plug it into the horizontal and say it spends 3.9 seconds going up and then back down to the landing area. While it's doing that, it's also going sideways 32.9 meters each of those 3.9 seconds for a total of 128 meters to the right. That connection that I've drawn right there, the 3.9 seconds, I mentioned this in the lecture video. That's a big part of projectile problems, is being asked to calculate something in either the x or the y, and you don't have enough information to do it in the x or the y until after you solve for time in the other dimension. So you'll have to solve for time in the y and then plug it into the x, or vice versa. And usually you're not told that. You know to do that because you're taking physics. Okay, example number 3. How far away will a cannonball land? And notice land is in quotes there because it's not going to hit land. It's going to hit water or possibly a pirate ship, according to this drawing. If the cannonball is fired 195.2 meters per second from the top of this 32-meter tall cliff, and the cannonball is angled upwards at 21.1 degrees. So just like the last problem, I'm given the initial velocity, 195.2 meters per second, but I can't use that in my calculations in the horizontal or in the vertical. So the first thing I'm going to want to do is determine how much of that 195.2 meters per second is in the x direction. According to this, 182.1 meters per second of it. And how much of it is in the y direction? 70.3 meters per second. This is a really good idea to sketch the v initial on the drawing, but you have to remember that the v initial direction is not the direction that the object will continue moving in. The object will travel in an arc, and v initial just points out at some initial direction. The value of drawing v initial at that angle is to help you make the right triangle to calculate what I just did here. Okay, we're now to the point where we can list the givens. My givens in the horizontal direction are that there's no acceleration because it's a projectile, and the v initial is 182.1 meters per second, which is the average velocity and final velocity in the x direction too, because there's no acceleration. So the x direction is usually the easiest direction for the math for projectiles. There's not a whole lot going on. In the vertical direction, I know the acceleration because it's a projectile. I know v initial in the y direction because we just calculated it with some trigonometry. And I know that it starts at the top of this cliff and then splashes down into the water 32 meters below. I just don't know how far away from the cliff it'll be. So delta y is negative 32 meters. I need to determine how much time. No, I'm sorry. I need to determine how far away it is. So I need to calculate how far away it is in the x direction. It seems like it's pretty easy, right? I could just say the velocity in the x direction equals the displacement divided by the time. Like I just said a few seconds ago, what's going on in the x direction is really straightforward most of the time. I could just say delta x equals the velocity in the x direction, 182.1 meters per second, times delta t. But I don't know delta t. So this is what I was talking about when I say you're going to have to calculate delta t in the y direction and then plug it back in on the horizontal side to determine how far the cannonball went in the x direction. So I go over to the y and I say I know the acceleration, v initial, delta y. I don't know delta t. I could use that equation with the 1/2 at squared. There's nothing wrong with using that equation here, but it turns out that if I do that, I would be using the quadratic formula to find t in this particular problem. Sometimes that's the case, especially when there's a v initial. I could do that, or I could do it a different way that I'm about to show here, which avoids using the quadratic but involves more steps. So what I'll do is I'll say I'm going to use the time-independent equation. I know acceleration and vy initial and delta y. I don't know vy final, but I could find it this way. I wasn't asked for vy final, but once I determine vy final, which is plus or minus 72.5 meters per second, I know it's got to be pointed downward, so it's a negative 72.5 meters per second. I'm pointing out that it's a plus or minus because that's what happens when you take a square root. So this is where your negative comes from, is when you take the square root, it's probably on your calculator, it'll say 72.5 meters per second. And you need to know, oh, v final is going to be pointed downward, so it's a negative. Once I know that, I can then determine acceleration equals delta v over delta t. Therefore, delta t equals delta v over acceleration. And I can plug in the v final I just found minus the v initial I had found earlier, divided by the acceleration due to gravity. And I get, without the quadratic formula, that the amount of time this cannonball is in the air is 14.6 seconds. And so now that I've calculated delta t to be 14.6 seconds, I'm going to take that over to the left side of this slide and I'm going to substitute it in place of those three question marks. Delta x is then 182.1 meters per second times 14.6 seconds, so 2,653 meters. Which may seem like a lot, but that's pretty realistic. Cannons can fire things pretty far. I should mention that if you fire something fast enough, it will go far enough in the x direction that the curvature of the earth would matter. We're not going to do that types of problem, but I do want to mention that that sort of thing does exist. For the most part, we'll deal with smaller numbers so that things aren't traveling kilometers per second. All right, let's do a fourth example here, and I think this will be our last one for today. So a golf ball is resting on the ground. It's struck by a golf club and given an initial velocity of 50 meters per second at an angle 30 degrees above the horizontal. Before I even read the rest of the problem, I know I'm going to have to break that 50 meters per second into an x and y component. The ball travels toward a fence, which is 12 meters high, and it's located at the end of the golf course. The fence is 200 meters away. This is a lot of information. I'm going to need to draw this to make it make sense to me. Okay. Neglect any air resistance that may be acting on the ball. Calculate the amount of time it takes the ball to reach the plane of the fence. Will the ball hit the fence or pass over it? Justify your answer by showing your calculations. All right, let me start with a sketch and listing the givens. There's my 50 meters per second at a 30 degree up angle. I've drawn in the Vx initial and Vy initial components that I'm going to calculate. And I've got my 200 meters delta x and my 12 meter tall fence delta y. In the horizontal direction, I initially know the velocity x initial is v initial cosine theta, so 43.3 meters per second. The acceleration in the x direction, it's a projectile, so after it's been hit, it has 0 acceleration, and then how far it's going is 200 meters. In the vertical direction, we have that the V initial is VI sine theta, so 25 meters per second, and the acceleration is negative 9.8 meters per second. And they want to know how much time it's going to take to hit the fence. Okay, well, I know that the velocity in the x direction is equal to the displacement in the x direction divided by time, and I already know the velocity in the x direction and the displacement in the x direction. So I should be able to calculate the time by rearranging this and saying it's traveling 200 meters divided by 43.3 meters per second, so 4.6 seconds. That seems pretty straightforward, not too bad. The second part of the question was, is it going to clear the fence that's 12 meters tall at the other end of the golf course here? So let's take a look. What I really want to calculate is when it is 200 meters out at 4.6 seconds after it leaves the golf club, how high up is the ball? And that'll tell me whether it actually goes over the fence or not. So I can do this. The delta y equals Vy initial delta t plus 1/2 at squared. This equation is really, really useful in a lot of circumstances. I don't want you to be scared away from it just because I said it sometimes requires the quadratic. It only requires the quadratic when you're calculating delta t, and even then only sometimes finding delta t. If you have delta t and you're using it to find anything else, then you're not going to use the quadratic, and it's pretty straightforward. Delta y is the Vy initial, 25 meters per second, times the time we just calculated, 4.6 seconds, plus 1/2 times negative 9.8 meters per second, times 4.6 seconds squared. We're going to be really careful with all of our math here. Make sure we square what we're supposed to and keep the negative where it's supposed to be. And I don't know why that line is in there twice. That's funny. But I calculate that delta y is 11.3 meters, meaning that the golf ball will be 11.3 meters above the ground at 4.6 seconds after it's been hit, which is when it's 200 meters away in the x direction from where it's been hit. So the answer is no, it doesn't make it over the 12-meter tall fence. It is only at 11.3 meters high. It hits the fence. Okay, that's 4 examples on projectile motion, and those are the only ones we're going to do today. But we'll have more in our practice problems, and we might come back and do some more of them as part of a test review for next week.